Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this example, we have this configuration here where a metal bar is falling and it's making contact with these two metal plates here on the side. And when it makes contact with these plates, it completes this circuit we have that's connected to this resistor up top here. And as it falls, it's also in this uniform magnetic field. So it's getting some sort of induced EMF across the bar here, and consequently causing a current to run through our circuit. So we're basically using the force of gravity to generate a electric current. So what we want to know is, given the speed at which this bar is falling, the strength of the magnetic field, the length of the bar, and the resistance of our resistor in our circuit, we want to know what the mass of the bar is going to be if it's at static equilibrium, so it's just falling at a constant velocity. And then we're going to look at some stuff regarding the where the energy is going in this problem after that. So first, let's just try to figure out what the mass is. So I just said a moment ago, this is this bar is in static equilibrium. So what that means is that the sum of all forces on the bar is going to be equal to 0, right? So Newton's second states that sum of all forces is equal to ma, and if there's no acceleration, then the sum of all forces is just equal to 0. So in our case, what forces are canceling each other out here? Well, we know we have the force of gravity, just mg, pushing down on the bar, and we know we have some force pulling the bar back up, which we'll just say it's the force, some magnetic force is keeping the bar up, which is a result of our induced EMF. So we know that this force here is really just the force on a rod that has a current in a magnetic field. And the force on a metal rod with a current in a constant magnetic field is just I times L times B times the sine of the angle between the direction of the current and the magnetic field. So if the current is parallel to the magnetic field, then there's no force. So because we have this induced EMF, right, we get a current. And since we have a current, we're going to have a force on our wire here, or our rod. So in our case, the angle is just 90 degrees. So the sine of 90 is just 1. So we really just have I times L times B. So if we refer back to our Newton's second here, the sum of all forces is going to be the magnetic force on our rod here with a current in it, minus the force of gravity, and this will be equal to 0. Or if we move mg over to the other side by adding it to both sides of our equation and substituting in for the magnetic force here, we'll have ILB equals mg. And we can divide both sides by g and just have m isolated. So we have m is equal to the current times the length times the strength of the magnetic field over g. Okay, so we don't know what the current is in our bar, but we can substitute out for it. So if you recall Ohm's law, V equals IR, for our circuit, we will be able to just solve this for I, replace V with our EMF, since that's the voltage in our circuit. and we'll just have I is equal to the EMF over R. So we can substitute that in. We'll have that the mass is equal to the EMF times L times B over RG. So we're getting closer now. We don't have the EMF, but again, we can recall that the motional EMF for a metal bar in a constant magnetic field, given that the length of the bar, velocity of the bar, and the magnetic field are all perpendicular to each other, is just going to be V times L times B. So if we substitute that in, we'll have that M is equal to V L squared times B squared over R times G. So now all of these are known quantities, right? We have the velocity, length, strength of the field, resistance, and gravity. It's just 9.81 meters per second squared. So these are all in the correct units, it looks like. So we can just go ahead and plug them in. And if we plug them in, we're going to get a mass of 0.23 kilograms. So again, key thing to that part of the problem, we were in static equilibrium. There was a force of gravity on our bar. There was a magnetic force on our bar opposing it because of the induced EMF in our bar causing a current, and a current in a magnetic field will cause a force. So these two forces were opposing each other such that the bar was going constant speed. So we could just use Newton's law and some stuff we know about circuits and motional EMF to find the mass. Okay, so now we're going to look at some energy considerations. The first thing we want to find is what the change in gravitational potential energy is in 0.2 seconds. So let's look at the change in U, gravitational, in 0.2 seconds. So the thing to realize here is that if we write down the conservation of energy for our system here, we'll have that the change in our potential and the change in the heat dissipation by our circuit, we'll just call it energy of heat, should be equal to 0. Or since the change in our heat, initially we have no heat, right? And then we end up with some after the bar goes down a certain amount. We'll just end up with the fact that the change in potential energy is equal to the heat dissipation of our circuit here. Or if we think in terms of power, that is, if we divide both of these by a change in time, we can say that the rate at which we lose potential energy, right, gravitational potential energy, is the same at which we dissipate power in our circuit. And of course, the power dissipation in our circuit is just going to be the EMF squared over R, where the EMF is just the motional EMF, right? So again, which is equal to just V times B times L. And the reason we wanted to express this in terms of powers like this, in terms of energy per second, is because we're given a time here. And we know that if we multiply a power times a time, we'll end up with our energy. So if we substitute in for our EMF there, we'll have VBL squared over R is equal to the power dissipation in our circuit. And if we multiply that times delta T, we will have our change in potential energy. So delta T times PG equals delta T times PC. which is equal to delta T times that big expression over there. VBL squared over R. Okay. So at this point, we can just start plugging in values again. We've got our V, our BRL, our time interval, and our resistance. And if we do that, we will get that the change in our potential energy is going to be equal to minus 1.8 joules. And I've added the minus sign on this because if you think about our initial potential energy versus our final potential energy, after we drop, right, our final potential energy is going to be less than our initial potential energy. So this U final minus U1 is actually going to be less than 1. Or sorry, less than 0. All right, now what we want to figure out is how much electrical energy was dissipated in 0.2 seconds. Well, lucky for us, we actually just answered that question, right? Because the rate of energy dissipation in our circuit, we said was equal to the rate at which we transferred our potential energy into our circuit. So this is going to be the same as, and these are magnitudes. So this is going to be the same as delta U up here, except with a different sign. So if this was the change in potential, the energy dissipated by our circuit, EC, is just going to be the same thing except with the positive sign. So there you go. We just determined what the mass of our bar in this system is. And also, via conservation of energy, we determined that since the potential energy, gravitational potential, is getting converted all into heat dissipation in our circuit, that we were able to figure out how much gravitational potential we would transfer into our circuit in 0.2 seconds. And because we knew that was equal to the rate of dissipation of energy in our circuit, we could say that it had the same value in energy just with a different sign.